Hello again. So, as promised, we're now going to be talking about absolute maximums and minimums. So, last video we talked about critical points, and finding absolute maximums and minimums is going to be involving first finding the critical point and then using that to find where you have an absolute max or minimum. Okay, so let me jump right in and set up an equation or a problem, and then I'm going to have to stop and explain what the process is going to be. So first, let's say that we are trying to find the absolute, let's say we're going to be finding both absolute max and absolute min of the equation 2x squared plus 3x plus 6 on the interval 0 to 2. So find the absolute max and min of this function on the interval 0 to 2. Okay, so there's going to be an important theorem that we can apply to absolute max and min problems. And if the theorem doesn't apply, then finding the absolute max or min is going to be much more complicated. You'll probably never see a problem where this theorem doesn't apply, but let me describe the theorem. So if you have a continuous function on an interval like 0 to 2, then it is guaranteed that your absolute max or minimum will exist, and furthermore, the absolute max or minimum is either going to be at one of your two endpoints or some critical point that is in between your two endpoints. Okay, so the reason for this is because if you had a continuous function between two endpoints, A and B, like this function, for instance, notice that we have like, this is the absolute min, it's the smallest point anywhere, and that's the absolute max. The absolute max and min are occurring at the endpoints. But we could have another graph where the function does something like this, and then we have an absolute max at a critical point, because a critical point is a place where the slope is 0 or undefined. So, but if the function was not continuous, so if the function did something like this, then, actually, technically speaking, that is a critical point because the point exists right there, and so the derivative is undefined, and the point exists and the derivative is undefined because it makes a jump discontinuity. Right. So here is an example of that absolute value theorem I was telling you doesn't apply, but still there's an absolute maximum there. But normally problems where the function's not continuous, it won't always guarantee an absolute max or min. And that's what the absolute max or minimum theorem is saying, is that when you have a continuous function, it's an absolute guarantee the absolute max or min will exist, and it'll be at a endpoint or a critical point that is in between your two endpoints. Like here, if, let me make this a little bit clearer. So what if we had that function? This function, it's not continuous, and notice there's no absolute max. That's because I didn't fill this circle in with a solid dot. That means that the function may be approaching a certain value, like maybe that's 9, and it gets closer and closer to 9, but it never actually reaches 9 because I didn't fill in the open circle with a dot. Therefore, there is no absolute maximum. Like someone might say, well, we have an absolute maximum of 9, but show me where is the function equal to 9? It's never equal to 9, so you can't say that 9 is the absolute max. Well, you might say, well, maybe the absolute maximum is like 8.99. Well, the function actually gets even higher than 8.99. It gets really, it gets close to 9, and never stops getting closer to 9. So 8.99 is not the absolute max because it eventually reaches 8.999 or 8.9999. So there is no absolute maximum for this function, and this was a non-continuous function. As I said, we're probably not going to be dealing with non-continuous functions. So for continuous functions, we will always have an absolute max or min, and it'll either be at one of the endpoints or a critical point in between. So step one, find your critical points. Okay, so if we take the derivative of this, we get 4x plus 3. Critical points are going to be whenever the derivative is either 0 or undefined. So this derivative is equal to 0 when x is -3/4. And that's the only critical point. I should have checked to make sure this point exists in the original function, but polynomials exist everywhere, so this is a critical point. But -3/4 is not in between 0 and 2, and the absolute max or min theorem says that when the function is continuous, polynomials are continuous everywhere, then your absolute max or min has to be at one of your endpoints or a critical point in between. This is not in between, so it's sort of irrelevant. So all I have to do next is find the values at the two endpoints. There's no critical point in between. So just let's look at the value of your function at 0 and 2. If we plug 0 into the original equation, we get 6. If we plug 2 into the original equation, we get 8 plus 6 is 20. Therefore, 20 is the absolute max. You would say that you have an absolute maximum of 20. And the lowest point here is 6, so we have an absolute minimum of 6. Be very careful whenever they're explaining like what the maximum minimum is. If they say the absolute maximum is, or an absolute maximum of 20, that's the y coordinate. That's the value of f of x. If they ever say that you have an absolute maximum at x equals 2, then that's the x coordinate. So if they use the word at, like absolute maximum at 2, they're meaning x equals 2. If they say absolute minimum or maximum of x equals 20, they mean the y coordinate is 20. That's the maximum value of the function. So just be careful. If they're using the word of, they're referring to the value of the function, which is the y coordinate. If they're saying at, then that's the value of the x coordinate of your function. Okay. Let's make this problem. I'm going to change a little bit so that this is a little bit more interesting. Okay. We already know this function has a critical point at -3/4, but my interval didn't include -3/4. So let's change the interval so that it now includes -3/4. So now let's try to find the absolute maximum or minimum on the interval -1 to 0. So first step, find the critical points. Critical point is at -3/4. That's now in between -1 and 0. And then I need to look at the value of my function at my two endpoints and my critical point, because now it's in between the two endpoints. Now I just need to plug in all three of these into the original function. Whatever gives me the lowest value is the absolute minimum, and whatever gives me the highest value, well, that's the absolute maximum. Okay, 0 is 6. Plugging in -1, we get 2. -3 is -1. Plus 6 is 5. Okay, -3/4. F of -3/4 is 2 times, and then -3/4 squared is 9/16. Plus 3 times -3/4, and then plus 6. So we get 18/16 minus 9/4 plus 6. I can reduce that fraction down to 9/8. Let's also get these to be 8s in the denominator. So multiply the top and bottom of this by 2, and multiply the top and bottom of this by 8. So positive 48 plus another 9 is 57. Minus 18 is 39/8. Okay. Now 39 divided by 8, that's almost 40 divided by 8. So that's almost 5, but it's a little bit less than 5. Therefore, 39/8 is the absolute minimum. and 6, well, that's the biggest value, so that's the absolute maximum. So we have an absolute minimum of 39/8 and an absolute maximum of 6. Okay. Maybe let's do one more example of finding absolute maximums and minimums. Okay. Let's do a function that involves some trig stuff. Okay, so let's say f of x is cosine squared x. Okay. Plus sine x. And let's say that we're trying to find the absolute maximum and minimum on the interval -pi/2 to +pi/2. Okay, so find the absolute max and the absolute min on that interval. Okay, well, sine and cosine are defined for all points. So any critical point, like any place where the derivative is either 0 or undefined, I automatically know is going to be a critical point because this function is well defined everywhere. So let's find where the derivative is 0 or undefined by taking the derivative. Okay, by the chain rule, we bring down the power, we reduce the power by 1, and then we multiply by the derivative of the insides. The derivative of cosine is negative sine, and then the derivative of sine is positive cosine. Let's factor cosine of x out of both of those. That leaves me with -2 sine x plus 1. And then this derivative is equal to 0 with either of these two factors equal 0. So either cosine of x equals 0 or -2 sine x plus 1 equals 0. So now I need to solve these two little trig functions. Well, cosine is on a unit circle the value of your x coordinate. So think on a unit circle, when is cosine equal to 0? That's when your x coordinate equals 0. That would be up here and down there. So that would be at the angles -pi/2 and +pi/2. Those would both be critical points. As well as if you add 2 pi to either of those, you get other critical points. But actually, in between the region -pi/2 and +pi/2, these are already your two endpoints. So we haven't succeeded in finding any critical points in between our two endpoints yet. But let's look at the other equation. So if we solve for sine of x, we get that sine of x needs to equal 1/2. Okay? Well, I remember from memorizing my 30, 60, 90 degree right triangle that sine of 30 degrees is 1/2. So one answer is 30 degrees. Now also on the unit circle, it's when your y coordinate equals 1/2. So that would be here at 30 degrees or pi/6 radians, but also over here where that's 30, which makes the angle 150 degrees. That's 5 times 30 is 150. Therefore, it's 5pi/6. Okay? And once again, if you added 2 pi to either of those, you get other answers. But the only angle that's going to be between -pi/2 and +pi/2 is just the pi/6. See, that's bigger than pi/2, which is straight up. So pi/6 is the only critical point we are actually interested in that is in the interval. Okay, so that was the first step, is to identify our critical points. Let me just put that our critical points were at -pi/2, +pi/2, and also at pi/6, 5pi/6. The dots are just indicating there's also more equivalent angles that would also be critical points. But the only critical point that is in the interval -pi/2 to +pi/2, not including the endpoints, is the pi over 6. So now we need to make a table of values that include our two endpoints and the only critical point that is in between the two endpoints. And then plug these into the original function. Okay, negative pi over 2, that's straight down on the unit circle. Remember that sine is your y-coordinate. The y-coordinate would be -1. Therefore, this is -1. Cosine is your x-coordinate. Straight down, your x-coordinate 0. So that's 0 plus -1. Pi over 2, well, that's straight up on the unit circle. And sine is your y-coordinate, so that would be +1. This is still 0, so you wind up getting +1. Now for pi over 6. Let's write down that triangle that I erased, the 30, 60, 90-degree triangle. Okay. So when we plug in pi over 6, cosine of pi over 6, well, that's the same as cosine of 30 degrees, is √3 over 2. And then the √3 over 2 winds up getting squared, which is going to give you 3/4. Plus sine of x, well, sine of x is 1/2, so plus 1/2. 3/4 plus 1/2, which is 2/4, is 5/4. 5/4. Therefore, the absolute max is 5/4, and the absolute min is -1. All right, so that's going to be it for today. Next video, we'll be talking about local maximums and minimums, and how the approach is going to be slightly different, but it will still involve finding those critical points first. And then instead of making a table of values, which we do for absolute max and min, we'll instead be doing something called a sign chart on a number line. Anyway, that's going to be next video. Hope you all are having a good day, and see you all next time. Bye-bye.